Hello and welcome in. In this video, we will be looking at a strategy for how to find our empirical and molecular chemical formulas, starting from experimental data. Maybe this is the mass percent for the different elements in our compound, or maybe this is starting with the gram amounts of each element in our compound. This is an important technique. We need to be able to look at the kind of relative composition of our compound and figure out what is the chemical formula. Our strategy is based on, well, the information that is provided in our chemical formula. Our empirical formula is going to tell us the simplest ratio, the simplest whole number ratio for the elements in our compound. This is not in terms of grams, but it's in terms of the number of actual atoms, or the simplest ratio for the number of atoms. Or if we want to scale up, it can be the ratio of moles for each element. In our compound. Now this is important because, well, we want to have this mole ratio. We want to know how many moles of maybe carbon are present for every mole of hydrogen or vice versa, so that we can put this into the subscript in our chemical formula. But in the lab, we don't really have a direct way to measure the moles of our elements. What we do have are ways to measure the gram amounts of our compound, the gram amounts of our elements. Right? We can put things on a scale and measure their mass very quickly. In order to get this kind of weight information, this mass information, into a useful form for our chemical formula, we need to get to moles. So that can be our first step. Switch from grams to moles so that we can put that ratio into the subscripts in our chemical formula. That can't be our final answer unless we end up with the simplest whole number ratio. To do this, we can have a quick mathematical trick. We can scale our ratio by dividing everything by the smallest value that shows up. And then if necessary, we can scale again, multiplying up to get rid of any decimals, get rid of any fractions. From here, if we ultimately want to end up with our molecular formula instead of the empirical formula, we need one extra piece of information. To find our molecular formula, usually we have to measure its molar mass in addition to having that empirical formula. We have a formula that we can use. We can find this scaling factor to convert between our empirical and molecular formulas. Remember, our empirical formula is just scaled down from our molecular formula by some whole number. Right? The molecular formula, we can look for any common factors in our subscripts and scale down by that common factor. That's that number n. The key here is that when we scale our formula down, we're going to scale the mass of that formula down as well. And so we can use this n is equal to actual molar mass compared to the empirical formula molar mass to figure out what we need to scale by. I like to represent this as kind of a table to organize our thoughts effectively. And so if we're looking at our empirical formula, we can get this using the strategy on the previous slide. We can get the molar mass for our empirical formula just by using the periodic table. We are ultimately trying to find this piece, to find that molar mass, to find that molecular formula. And we are given the molar mass of our molecular formula. That's the extra piece that we have to measure or find out. To go from our empirical up to our molecular formula, we have to have this scaling factor n. And if we know these two numbers, we can use that. We can use essentially this formula to solve for n. All right, what does this look like? Well, here are a couple of practice problems. So here we find 24.5 grams of nitrogen and 70.0 grams of oxygen. This is nice. We have the mass amounts of each element in our compound. But what we need to do to get our formula, we want to figure out what this ratio is to fill in for x and y in our chemical formula as written up here. These x's and these y's, they have to be in terms of moles and not grams. Right? Our chemical formulas are mole ratios, not grams. So for each of these, let's cancel out grams and try to get to moles. This is the molar mass, but flipped upside down. So we can look this up off the periodic table. 1 mole of nitrogen weighs 14.01 grams. Oops, typo here. 1 mole of oxygen weighs 16.0 grams. And so we can get these numbers. And I'm going to keep a lot of decimals for a moment. All right, these numbers are good enough to plug into our chemical formula up there. The problem is it can't be our final answer, but it is the right ratio. Right, we could put n 1.7487, 4.375. Our units are okay, but to be a good empirical formula, we have to be the simplest ratio, the simplest whole number ratio. So we can do one extra step here. We can scale these by dividing each of them by our smallest value. Here our smallest value is 1.7487. So let's scale this ratio down by dividing by that, dividing both of them by this. This is a good math trick because we're looking for whole numbers. And there we go. We have at least one whole number. 1 mole of nitrogen. Anything divided by itself is just 1. Our second number, hopefully will end up close to a whole number. And, well, not a whole number, but something we can work with. 2.501 moles of oxygen. So now we're getting closer. Now we have, okay, 1 nitrogen for every 2.501 oxygen. One of our subscripts is a whole number. We need to do one extra step to get both of them to be whole numbers. What I like to do is to think of these as fractions instead of decimals. So this is approximately 2.5. And if we want to scale a fraction up to be a whole number, we want to multiply by whatever our denominator is. So let's scale this by multiplying by 2, scale this by multiplying by 2. We end up with 2 moles of our nitrogen. Pardon me for going to the other side. And 5.002 moles of oxygen. I've been keeping a lot of decimal places, keeping a lot of significant figures here. We get to round at some point, and my rule of thumb is you're able to round if you're close to a whole number out to 2 decimal places. So 0.00, yeah, we can round this to just 5 moles of oxygen. If you had 5.1 instead of 5.0, maybe we'd want to do a different multiplication step. And so here we go, our final answer here. N2O5. This is our nice empirical formula. Recapping real fast, starting with these gram amounts, we can switch everything to moles and then do a little bit of dividing and multiplying to get our mole ratio to be simple whole numbers. Follow-up question. We know that the molar mass here for our actual compound is 216 grams per mole. We want to find this piece. We want to find the actual molecular formula instead of this empirical formula, N2O5. Well, what we can do is look up the molar mass for our empirical formula. So about 28 for our nitrogens and 5 of these oxygens. All right, our molar mass here, 14 plus 14 plus 16 times 5. Yeah, we get about 108 grams per mole. The idea here is that our molecular formula is some number of these empirical formula units. Maybe it's just one of them, maybe it's 2 of them stapled together, maybe it's 3 of them stapled together. That the number of units stapled together is this n value. And this scaling factor n, it's related to our formulas, is also related to how heavy these formulas are. And so to go from 108 up to 216, we need to multiply by 2. And so for our formula, we also just need to scale our formula by 2. And 4, O, 10. And so there we go. With our empirical formula and with the molar mass of the entire molecular formula, we can figure out what our actual molecular formula is. Hopefully this has been helpful. If you have any questions, let me know. Otherwise, I'll see you all soon.